We're going to have a look at worksheet number 6, specifically questions 3, 4, and 6 on worksheet number 6. Number 3 says, here's my electric force acting between two charges, both of this magnitude. What's the distance between the two charges? We're going to say, for this one, the force, the magnitude of the force at least is 7.19. And we're going to say the charge Q1 and Q2. See what I'm doing there? Saving myself from writing the number twice. I'm just saying Q1 is equal to Q2, and that's equal to 2.00 times 10 to the negative 10 coulombs. We're looking for R. My equation is the Coulomb's law equation. F is equal to K Q1 Q2 over R squared. Now we've got to rearrange this to solve for R. Take the R squared up by multiplying. You've got to solve for R, so what do we get rid of now? Yeah, we're going to divide it by the force, right? Divided by the force, we get R squared is equal to K Q1 Q2. And then we're going to say R is equal to, how do you get rid of the squared? Yep, so it's going to be the square root of K Q1 Q2 over F. We have all these numbers now. Remember, K is 8.99 times 10 to the 9. It's on your data sheet. I'm going to assume you can sub those numbers in. If you can't, let me know. When we do, we end up getting a value of 7.07 times 10 to the negative 2 meters. 4 says two identical charges are separated by a distance of 1 meter. Here's a repulsive force. What's the magnitude of each charge? This is a tricky one. How many people think they got this one? I gave you the answers. How many people did get this one? Good. Not bad at all. This is a tough question. Our separation distance is 1 meter. That's the easy part. There's a repulsive force of 3.6 newtons. That's also the easy part. We're looking for Q1 and Q2. But because they're identical, why don't we just call them the same thing? Instead of calling it two different variables, let's just call them both Q and solve for the value of Q. Now, my equation is the Coulomb's law equation. It's K Q1 Q2 over R squared. But if I replace Q1 and Q2 with Q, what does this equation become? F is equal to K times what? 2Q? Q squared. Q plus Q is 2Q. Q times Q is Q squared. So it's KQ squared over R squared. Now I'm going to rearrange this to solve for Q squared. F times R squared. How does the K go over? Dividing, yeah. F times R squared over K equals Q squared. And then what am I going to do to find Q? We square root it. Now you got to be careful here. Because of the numbers involved in this question, if you had said 2R instead of R squared, you would have still gotten the same base to the answer, 2.00. The answer is 2.00 times 10 to the negative 5. You would have gotten 2.00, I think, times 10 to the negative 10. But you may think you're correct because of the 2.00. It's not 2Q, it's Q squared. The only reason the base worked out to be the same in this case is because the square root of 4 is 2, and half of 4 is 2. Make sense? So it is Q squared. It absolutely is Q squared, even if you got 2.00 times 10 to the something else. It's just kind of got a little bit lucky on that one. All right, and the last one that I want to go over here today is number 6. Number 6 says, calculate the initial acceleration of an alpha particle. If the alpha particle is this far away from the electron and the alpha particle is free to move, what's the acceleration of the electron? One of these questions, hey, we know when we're looking for acceleration, whether we're looking for it once or twice like we are in this question, what do we got to have first? Yeah, the force needs to be with us. The force needs to be with us. So let's get the force. It's K, Q1, Q2 over R squared. It's 8.99 times 10 to the 9 times Q1. We'll make that the charge of the alpha particle. And Q2 will make the charge of the electron. Notice I did not sub in the sign of the charge for the electron, the negative. I never do in these equations. It's always just the magnitude. Divide that by r squared. 2.00 times 10 to the negative 25 squared. I would suggest getting the bottom number first, press equals on your calculator, and then get the top number divided by the bottom number. When I do this, I end up getting a force of 1.1507 times 10 to the 22 newtons. Now, a couple questions here. Firstly, why did I not round that? Why didn't I round that to 2 or 3 digits? Yeah, I'm looking for the acceleration. I'm not looking for the force, so this isn't a final answer. Okay, good. Secondly, which force have I found? The force on the electron or the force on the alpha particle? Alpha particle, you're correct. Anybody say the electron? It's both, yes. If an alpha particle applies a force on an electron, the electron applies an equal and opposite force on the alpha particle. So the force is the force. This is the one we want for both of them. Now that the force is with us, now it's time for Jedi Academy. Now that the force is with us, we need to learn what to do with the force. How do you use the force now that the force is with you? Anybody? Yep. A is equal to F over M. Newton's second law, A is equal to F over M, or F is equal to M times A. If you want to find the acceleration of the alpha particle, then let's use the mass of the alpha particle, which is on your data sheet. And that's going to be 6.65 times 10 to the minus 27 kilograms. And we do the math on that, it works out to be 1.73 times 10 to the 48 meters per second squared. That is a very, very, very large acceleration. That's okay. There's no upper limit to acceleration. It could be 10 to the 100. It's not likely to be that high, but it could be. There is a maximum speed, but there's no maximum acceleration. Now, you want to find the acceleration of the electron. We're going to do almost the same thing, except this time, instead of using the mass of the alpha particle, we're going to use the mass of the electron, which is 9.11 times 10 to the minus 31. When we do that math, using the same value for force, we end up getting 1.26 times 10 to the bigger or smaller than this one, the alpha particle. Bigger acceleration or smaller acceleration than the alpha particle? Bigger. And how come? Because it's smaller mass. If you apply the same force to a car as you do a train, the car will accelerate quicker because the mass of the car is smaller. Those are both right. The first one is the acceleration of the alpha particle. And the second one, Jacob, is the acceleration of the electron. You're looking for two different things there. It's like saying, what's the acceleration of the train, what's the acceleration of the car? Okay, let's take a look at one more example today, and then we'll call it a day here. There's example 3 on your example question sheet. Just find the net force on sphere B to spheres A and C. Let's label these A, B, and C, just so that we're all using the same frame of reference. Let's also circle this, 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 and this. Circle the units because they're non-standard, they're microcoulombs. And we know that, although we often see microcoulombs, we know that in a calculation we have to convert those to coulombs. We also know that that negative in front of charge C matters. Not in an equation, but it matters in terms of attractive or repulsive. So we're going to draw attention to that as well. Now, we want to find the net force on B due to A and C. So what I want you to do here is pretend, firstly, that you don't have object C. Doesn't exist. Okay, pretend object C doesn't exist. Let's worry about the force on B due to A, and then we'll take care of C. So, which way is B pushed or pulled as a result of A? These are like charges. A and B are both positive. Do they attract or repel? They repel, good. Now, if B is repelled by A, which way does it move, right or left? It moves to the right. It's pushed away from A. So we're going to say the force of A on B is to the right. Now, there is a force of B on A to the left, right? A gets pushed to the left. But that, But that's, yeah, exactly. It's an equal and opposite force. But we don't really care about that force in this context of this question because the question doesn't ask us what happens to A. It asks us what happens to B. Now, what about the force of C on B? B is positive, C is negative, right? Are they going to attract or repel? Attract. Then as a result of an attraction, is B going to get pulled towards C, or is B going to get pushed away from C? Pulled towards it, good. We're going to call that FCB. Now, C will be pulled towards B, right? But that's not relevant in this question because we're not looking for what happens to C, we're only looking for what happens to B. So let's get rid of that one. I don't need to draw that if it's not relevant. I've got FAB and I've got FCB. Now, what do you think I do next? You got to find each force, yeah. FCB is going to be KQC QB over R squared. It's 8.99 times 10 to the 9 times QC, which is 1 times 10 to the negative 6. Notice we dropped the sign of the charge in there, right? We never sub it into an equation. Times 3 times 10 to the minus 6. I'm not forgetting that exponent because I circled it in red. Divided by R, which is 1.50 meters. I'm going to square that. Go ahead. It's 10 to the negative 6 because the units are microcoulombs. And a micro is 10 to the minus 6 on our data sheet. Make sense? All right. We calculate this. We end up getting FCB ends up being 0.01198 newtons. Now, we're not done because we haven't accounted for FAB yet. FAB is going to be equal to Coulomb's constant, 8.99 times 10 to the 9, times charge A, which is 2 times 10 to the minus 6 coulombs, times charge B, which is 3 times 10 to the minus 6. Both positive charges, but it doesn't really matter because we plug positive in anyways, just as we did with FCB. Divide that by R squared, that's 2.00. That gives us a value of FAB of 0.01345 newtons. Now, what do you think we're going to do with those two numbers? Yeah, we're going to add them up. This is physics 20 problem now. Right, in physics 20, when you had more than one force, you said F net is equal to the sum of the forces. We're going to do the same thing here. The net force is equal to FAB plus FCB. FAB is 0.01345 newtons, and FCB is 0.1198 newtons. Yes, thank you. It is 0.011 there. I think it's 0.02543, rounded to 3 digits. 1, 2, 3 digits. Fourth digit is 3, so it rounds down. 0.0254 newtons. There's my force. Yeah, carry the unrounded numbers over. Yeah. Now, I want to point out something here before we move on here. Had I subbed in the sign of the charge up here for charge C, right in here, I would have gotten a negative value for this force, right? And what would you have been tempted to do when you combine those forces? Add the negative, right? That's why I tell you don't sub in the sign of a charge. For us, a negative is supposed to mean left or down or south or west. We don't want it to mean something else. If we start mixing and matching sign conventions, like if we put the negative in beside the 3 there, like we've done, then it's going to get confusing. So I'm telling you, just leave those out. Leave those out. Get the magnitude of the force, And if one of them is to the left, make it negative. If both to the right, make them positive. Don't just say, oh, I got a negative force because I had a negative charge. Let me just add those together the way that they appear there. Okay? Does that make sense?